Alrighty then. Well, that was a happy clap. I could feel it in my hands, among other places. Yes, yes. But I guess what's going on? Memes here. Yes. And we are now, I believe it was like something like episode 18 of hashtag MML. What's that? My Monastery Life. Said MML, right? Not MLL. Those large language models are on the brain. I just got done listening to Professor Wolfram talking about their new AI chat assistant there that's built into whatever the most updated version of the Wolfram language is. Not a price and participation may vary. I believe it's free for any current users. But the long story short is, I think Clippy would be proud. You remember that paperclip back in the day? For those of us that are ancient enough that remember the little paperclip in the old Windows system that would just pop out of nowhere and be like, "Hi, could I help you?" And occasionally it might be useful, but it just seemed to pop up at the worst times. You're like, no, no, I'm struggling with something. You're recommending the wrong thing. Allegedly, it might actually work better this time. But I digress. Oh, hey, Griswold. Good to see you, my friend. Hopefully, we're not going too much off the rails of a crazy train. Well, that may come later. But I'm going to let other folks roll on in and everything. As you can see, there's a whole bunch of mumbo jumbo on the board back there because over the weekend we spent a little bit of time and we're going to go over. Don't worry, this shouldn't mean anything to you. If it means something to you, please let me know what it means. Okay. So what we're going to do is we're going to go over some random things on the board, things that one would do at like a physics monastery if when it's trying to figure out what might actually be going on, so to speak, with our realm of persistence, or what we may colloquially refer to as universe. Okay, that's a very broad claim, but that's not the title of today's talk. The topic is how I learned the impossible. Okay, and I'm using impossible in quotation marks because that's something that we throw around a lot. Oh, that's impossible. Now, do we actually mean that that is impossible or it is improbable? The reason why I say that is because randomly out of the blue, a 7 foot tall flaming gummy bear could crash through the ceiling right now, and that would be the end of memes. Now, that's unlikely. It's not impossible. Like, oh, there's some candy thing going on in California. They're going over, and then there was some tremendous malfunction. God forbid the plane all of a sudden explodes. Terrible things happen. Lives are lost on the giant thing that they were having in case. The case was shredded and everything. It catches on fire and it crashes through the roof, and that's the end of memes. Okay, that is highly unlikely. Still possible. Okay. Now, why am I bringing this up? The differentiation. Because very often in modern parlance or the verbiage, the words that we often use now today, especially on the internet, people have a habit of saying things. And I think a lot of folks forget about rule one of the internet. Rule one of the internet: don't believe everything on the internet. I feel like that would make many people's lives a lot better. Then again, I am not a psychologist, but we'll digress for now. And what I'm trying to say is, well, sometimes they say, "Oh, you can't do that. You can't figure that out." Oh, the fine structure constant. Nobody can calculate it because apparently Professor Dirac was very infamous when people were like, "Oh, Mr. Dirac, we have a new theory." He's like, "Can you calculate the fine structure constant?" And everyone's like, and walk away. It's no, 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 no. I say that from a very biased place because one of the first things that got my interest in everything is wait a second. This gentleman Thad appears to have a plausible explanation for why the fine structure constant is what it is. It seems to get it to all the known digits. Okay. And maybe it's giving us a clue that something interesting is happening here at a particular magnitude of our measurements. Things just don't seem to line up. Again, reference to previous talks when we were going over the ingredients of reality. Coincidentally, you only need five ingredients: time, space, charge, mass, and temperature. From those five dimensional ingredients, you can generate the constants in nature. along with appropriate mathematical operators. Uh, that's a whole bunch of words, means. You had the little tagline, stuff does things. Because that's exactly what I was just talking about. You got some dimensional ingredients, you got some stuff, and they're doing some mathematical things. Oh, that's not what it is. That not what's happening? I, I just say this, and I gotta give some shout outs here to Casey, Casey O'Keefe, Rick DeWitt, just because I've been blessed to meet some very smart people. And occasionally, when very smart people occasionally reiterate maybe just a little catchphrase, a little, maybe kind of a little bit of a trolly statement, because that's originally what it was. It's the stuff doing things. And oh, you can also invert that. That could be things doing stuff. Is there anything we else know? Any other states of stuff or things that may transform from one into the other by perhaps some method that we're not quite sure about yet? I'll leave that for the audience to decide. But and the reason why I say that is because this really hit me back during the pandemic and everything. A lot of different academics and stuff, they start doing things online. They'd be interacting. And shout out to Professor Keating. Uh, he he actually put out a public link on Twitter. You click on it, you go through the little Zoom thing to attend one of his graduate seminars for his graduate students. So I'm there. I'm like, oh, I'm learning some science stuff. I'm going to sit there. And then it was like being with a massive wall of text. Like I think a lot of people are. If you try to look at this, it's like, what is this? The square root of x squared minus y squared equals parentheses x squared plus y squared end parentheses. And oh, that's obviously a oneness gate. Okay, that might be true. But again, if you're a person, you don't have the background, you haven't seen a bunch of these things on a frequent and regular basis, it's going to be Greek to you, especially if you don't speak Greek. So, what I'm saying is, I was sitting in that lecture. I'm like, all right, I recognize C. I hope it means the same thing there. And they're going through all these calculations and everything. And I'm just sitting there. I am like literally bewildered. I'm like, I don't know what all this different stuff is doing, all these different symbols mean. So I'm just sitting there. I'm like, all right, let me compartmentalize. And this is called, I believe, chunking. I got this from my times and my semi-verbal verbal beatings I got from Jen and Duvid. Shout out to the Church of Entropy and Duvid. But it's basically you're chunking. It's like, all right, there's a bunch of stuff here. It's like, all right, I don't know what this stuff is, but we got some stuff. And if you were doing cosmology, it's like, all right, we've probably got some star stuff or stuff related to stars. Maybe it's distance. Maybe it's energy in some way. Maybe it's power. So like watts or something like that. It's in particular units. All right. So we got some stuff. We got some math symbols and stuff. All right. So it's doing a thing. Let me just put it at that. It's okay. I don't know what that is, but I just chunk. I'm like, all right, so that's doing like a distance measure here. Then we get over here. All right, this is some like metric for a mass system, not this right here, but I'm just uh personifying how I was taking that. So I'm sitting there and it's like, okay, well, that's based on that, that's based on this is there, but da, 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 da. And that led me to ask, I may have been the only question of the session, but it's like, um, to paraphrase, it was so how confident are we essentially if some of these things were a bit off, isn't that going to throw up the cosmic distance ladder? And to Professor Keating's credit, he's like, yeah, no, we could be wrong. It's like, listen, this is the best that we have based on the observational technology that we have in the time, the best interpretations that we have at this time. But yeah, no, there's going to be error in here somewhere, but we're trying to account for it the best we can. That's fantastic because that's science. Because science is the quest to be less wrong. Because if we know we are wrong, then we can seek to be less bad, less incorrect, less incorrect. I believe that's the PC, or at least a nice way of saying it nowadays. Okay, so to break it up, the way I learn what is impossible to me is All right, you sit there, you get immersed in it because science, like anything, especially since the different, so many different facets of science and everything, each discipline is kind of like its own language. When I was growing up, I took 4 years of Spanish, and I barely know a little Spanglish there. Me llamo Mateo Ricardo Zolo. What is that? Oh, I just said my name. I was on the paper the other day. Oh, okay. Yo hablo un poquito español. Un poquito, very little, much. Okay, but the reason why I'm sharing my foreign language, so to speak, education or lack thereof, is that I was always told growing up the best way to learn a language is to be immersed in it. AKA, if you want to learn Spanish, I don't know, maybe go to a place that speaks Spanish, Mexico. Go to Spain. You want to learn French because nobody speaks French except people that do. All right, it's okay. I still enjoy French slash freedom fries. Yes, I am that old to remember when we would say things like that. But if you're immersed in a language, well, it's kind of the sink or swim there. It's like you're going to learn to ask where the bathroom is. You're going to try to learn to get food. Oh God, what was that? What was that movie? It was the gentleman that got stuck in the terminal and everything there, and there was like a revolution in his country, so he didn't have a passport or anything. And oh God, famous American actor was, and I totally forget his name, but he learned. He's like, wait a second, I need to get food. My country doesn't exist. I can't exchange any funds. All my credit cards or anything is there. So he's like, wait a second, I can return little carts and I can get a quarter for each cart. So he's doing that and he's going to Burger King. So he can actually, it's, you learn to survive because I believe that's the story of humanity is to adapt and overcome. We learn so we can do better. Okay. So I've been blathering on for a little while. I'll check with the chat and then we'll go over just some little bit of explanation of what's on the board there. All right. Okay, we've got ooh, here's this comment. He's working out at H bar. Well, that seems like a place of action, my friend. But oh, hey, WWKK. All right. They're saying the Wolfram LLM assistant was Wolfram Alpha a moment again back in 2009. Because it very well might be because I've been using whatever the new Chat GPT thing is with like the coding assistant. And again, I only limited sample trying to have it do something with the Wolfram language to plot like, okay, put a sphere. All right, put it into a cylinder. Now fill it full of a water-like fluid. All right, now start spinning the sphere. I feel like that's in Modelica, an additional product. Probably could do something like that, or it's already built in. Uh, let's see here. Hey, Jax. Let's see. Uh, well, it's depends on how much time you have. Hey, Quant. And then we got well, if the Tibetans are postulating 5 elements for this realm, I mean, that seems to be a common thing because what is it? They did that for the Platonic solids. They thought that what was it? You had a tetrahedron. I think that was air. The cube was earth because duh. And then the octahedron was fire because it was kind of pointy and step on it and stuff, and it was bigger than the tetrahedron. And then you had water was obviously the icosahedron because it was mostly round like. And then you had the dodecahedron, the fifth platonic solid, well, technically like the fourth. Depends on how you want to contextualize it, but it's the largest volumetric platonic solid per unit one length. Yeah, I believe that's true. But so we have those 5 things. Now, were those representing the exact configuration? Doesn't look that way. Were they hitting upon something core, perhaps something primal? No, it's only 5 platonic solids in 3 dimensions. There's 6 in 4 dimensions. But hey, Tommy, what's going on, my friend? Yes, the Guinea Pig Collective is marching on through there. But okay, so how to do things that are impossible. Number one, the only way of determining the limits of the impossible is to go a little bit beyond them into the impossible. I learned that from Professor Keating because that's a quote from Arthur C. Clarke, and he runs like the Arthur C. Clarke Foundation. Uh, I think it's a really good quote, and I employ it fairly often, along with any sufficiently advanced technology is indistinguishable from magic. If you apply that, it's like people are like, oh, well, this is magic. This is magic. And then once people figure it out, well, duh, it was science all along. I just find that's very interesting. Maybe that's why games like Final Fantasy stuff did well, because they would be like science fantasy. You'd have you'd have the fantasy aspects. People would still be using swords and stuff, but then you'd also be utilizing high-end technology and stuff to do crazy things, not always for the best, because human beings, no one else has ever done anything bad before. But I guess I guess we're gonna have to see what happens. But okay, number one, impossible things are not necessarily impossible. I think we say that all too. Some things probably impossible. Okay, uh, getting human beings to all agree on all the same stuff likely impossible. Okay, all right. Hey, that's why I got out of politics and stuff, because when you realize a lot of these people just don't like each other, especially when you have backroom chats with a bunch of folks that you talk with. You boil it down, you boil it down, you do the Socratic method, you do the Socratic method, common denominator. I don't like that. It's not, it's an honest answer. It might not be a good answer, in my opinion, but it's at least an honest answer. When you have enough folks going like that, that's why it's like, well, there's a solution to this. It's a terrible solution. And that's why I'm like, should we legalize dueling? Question mark. It's an honest question. I think it might save a lot or just make things much more worse. If not, it would at least add a new dynamic about running your mouth on the internet. Because people like me don't do that all the time. I realize it would lead to my self destruction, but the world could probably use less people like me. Yes, that's a personal opinion there. At least a-holes. Okay, with which I am a group. Okay, so if many things that we claim are impossible are not actually impossible, they're just hard. Impossible does not equal hard. We often use that. Okay, so semantic rants aside, let's get to more stuff. Okay, so here's a board where we're trying to gain some more insight into what was formerly the hyperbolic vortex equation, aka the hyperbolic partition equation. Yeah, okay, get my hair in the way. All right. Well, as you can see, we're just listing partial properties. For me, I have more of a gaming background. Like gamer's probably one of the longest held identities that I have personally had. Okay, so as a gamer, whether you're playing Magic, you're playing Yu-Gi-Oh, any game, you're gonna have different characters, maybe a different card, and those cards would have different attributes. So whatever unit you are utilizing, there's going to be certain properties to it. Okay, and we're looking for properties of this partition equation here. What's that partition equation? This guy over here. We get our 1 over x plus x cubed divided by 2 pi. Is that equal to I raised to the j raised to the negative pi divided by 2 minus the magnitude of the Planck mass. Okay. What the heck does that all mean? Don't worry. Don't worry. Hey, we're still trying to parse, so that's why we have different details listed out. All right. So we got a 1 over x thing. Okay. So we've got some stuff. What's our stuff? We got some x's, we got some pi, we got ij, and we got an MP. Okay. All right. So we got some X stuff. So we got a 1 over X. Okay, I'm just going to use stuff and things interchangeably for flow here. That's also one of the reasons. For those of you interested in the deep lore, I totally stole that from Slugator. He was a YouTuber He covered Ark Survival Evolved back in Alpha. And I just remember you going around like someone in his show would be like, Slogator, what's going on? He's like, oh, just doing stuff and things. And I thought that was hilarious because I'm like, that's like the broadest statement you can make. It's like, what you doing? Stuff and things. Our stuff is doing things, or things, we're just doing some stuff. It's so broad, but with that broadness, now you can encompass what is going on into the proper category. Be like, all right, are we talking about math stuff? Are we talking about specific like Call of Duty stuff, Final Fantasy stuff, Breath of Fire stuff? I have a feeling Breath of Fire may return in a way that will make people happy. Or at least I would really hope to see that happen. Very biased. But all right, so we got some stuff. We got a 1 over x thing here. All right, so 1 over x. We said equal to y. Y equals 1 over x. So we get a hyperbola. It's a hyperbola, huh? It's this thing kind of going down like a parabola, but except you get like 2 of them. You could have a 2-sheeted hyperbola. Okay. And you got vertices over here. Here are their locations. Oh, in the center is 0, 0. The foci, basically, where you would actually place to actually start to draw these things. We got a whole bunch of root 2s. There's negative root 2s over there. There's positive root 2s over here. Because if you're going to put this in, you can get something like this. Okay. So we've got that stuff, and it's doing a thing. It's breaking into its little parts, and it's literally going to Wolfram alpha y equals 1 over x, and you get stuff like this. Okay. So we've got 1 over a thing plus a thing, x. What is that? That's your generic unit. This is what we are solving for within this equation. It's just our base thing. Okay. And to be fair, you could actually probably even put a 1 in front of that because that is 1 over. So we don't often consider the 1, and I think the 1 might be an important thing. So, and then what we got over here, we got this thing here. We got x cubed. Okay. So you think about length. You have length normally. You got, all right. You got a thing. We got a length. If we square it, oh, we literally square it. What if we cube it? Oh, we make a cubic thing. We have some term of a volumetric nature. And we're dividing it by circle, not 0. We should. Oh my God, I don't know how to make 0 into a. Here, I'll do this. Look, it's got a radius, or it's kind of like a Pac-Man here. All right, so we got our Pac-Man circled it. We got some volumetric element, an element of volume, a cubic element of volume divided by a circle. Cool. Now, again, don't necessarily know what that means, but at least we're attempting to parse stuff we might not understand. Okay. Now, in this whole thing, we've got it equal to, what is this? I raised to the j. You could do I raised to the I. It's going to, basically, we've got a plane. We've got like an orthogonal plane here. What could a plane be? We got a plane, but now it's going orthogonally out. All right. So we got another plane. So it's like, all right, we got a thing. Now it's got a rotation over here by like 90 degrees. Okay. And now we're going the other way. Where, well, seeing as these are the square root of -1, maybe we're going the same way. That's actually a good question. Which way does it go? Which way do we twist? See? Totally worth doing this already. All right. Should have been a question asked a long time ago. I didn't. I think that probably knows. Okay. So we've got some orthogonal twist, a 90-degree twist was being raised to -pi, divide by 2. All right, well, that's 2 pi. So that's like a big twist. We're going one way. And then we're doing a little twist going the other way. Okay. And now we're subtracting out something. So we've got like a gap. We've got a space between the stuff. Okay. What is the thing that we are subtracting out? It's the magnitude of the Planck mass. We're using that as, some may say, a gap in order to set a proper scale. Okay. What does this have to do with putting a proper scale or anything? Well, if you type this into Wolfram Alpha, you might have to just do I to the I. I'm not sure, because sometimes you have to leave a little note, be like I equals square root of -1, j equals square root of -1, k equals square root of -1, yada, yada, yada. But if you put this in and you solve it, you might need to just do Planck mass divide by kilograms to get the dimensions of mass out there to get its absolute magnitude. But if you do that and you compute it, you get a certain solutions. The solution to this, or at least the first solution, when you square it, you got the fine structure constant, the all known digits, like we did, I think, on last Thursday. Last Thursday, I think it was. Yeah. Um, and again, there are some more recent measurements that start to deviate by a good number of sigma from the Berkeley 2018. It's like, God, it's probably up around 7 sigma or so. I think the current fine structure constant we've been going with is about 7.5 sigma off. How can we be half 7.5 sigma? Well, coincidentally, with that sigma, we seem to have noticed a very interesting pattern going out. And if there was some deviation or something going along around the seventh decimal, significant decimal place for a lot of these constants of nature, maybe there's something we could learn. Maybe there's something very interesting going on there. We could just be wrong. And if we were wrong, we just need to divide that by root 2. And we literally get smacked down in like the most recent measurements. Literally, like it's scary how close it is uh, into the one standard deviation. It's like right in the center. It's kind of creepy. But hey, we're going to go with the data leads us. If that's where we need to go, that's where we'll go. We'll just have to do some recomputing. But a lot of that doesn't really make much of a difference until about the 7 significant digits. So um, even with the old convention of just straight 10 to the -7, doesn't affect calculations for H bar because we only get like 10 digits to that. Uh, C basically remains the same and everything. Yeah, most of the major constants. Because a lot of the major ones, we've cut off the extra significant digits and we're defining them at 10. Why? Because we have high confidence to 10 significant digits. After the 10 significant digit, the error seems to be a little wonky and it's uh, that may be a very interesting question. Maybe Professor Barondess's explanation using non-Markovian dynamics will help figure out what might be going on. I really need to start reaching out to people again, because those are some fascinating talks, and I really think it explains a lot. But okay, so when I say that this might be setting a scale by utilizing the Planck mass, because now if we're subtracting out, it's like, okay, kind of graphing that over here on this this Pokeball or slash Deadpool looking thing. So as we can see here in our in our Deadpool in the eyes, the lemon escape with the unit circle around it, and it does kind of look like Deadpool. It made me laugh. Mm. But okay, so if this is a gap, if we're using this to set a gap over here, okay. So what the heck? This is just some letters and numbers. What the heck does that mean? All right. You got a thing, you get the inverse of a thing, you get the volume of the thing, you're twisting it with a circle. Why? Because circles are important. And I think there's something within physics called the spherical cow. That's a term that you'll hear different folks like Professor Sean Carroll say. What are we envisioning? Idealistic conditions. Basically, we're assuming the thing is a perfect sphere. We know it's not a perfect sphere. It's kind of like, oh, spherical cow. When was the last time someone actually saw a cow that was a perfect sphere? A perfect sphere, yes. Yes, that's what we call it, a perfect spherical cow. Uh, I ain't seen it because, to be fair, I ain't never seen a perfect circle. Now, I've listened to a perfect circle, I believe, but as far as actually Seeing one, yeah, I think that's one of those platonic ideals. Uh, okay. Why was I saying that? Oh, okay. So if you're willing to grant a circle, we can continue. All right. We've got a thing plus one over the thing plus the volumetric thing divided by the cycle. We're setting it equal to an orthogonal rotation raised to another orthogonal rotation. And then we're twisting it back the other way via the unit of spherical curvature divide by 2 that time. And we're subtracting out what we're going to claim right now of the gap of the Planck mass. Some may say the Planck mass gap. Is that telling us something? Or is that even the right question? We're going to find out sooner rather than later, I claim. Okay. But, okay. So if we're using this to help scale, so we've got something for prime within our base Planck constants, one of our 5 base ingredients of reality. And we're using mass to help calculate, at least for the first answer, because you get 4 answers. And that might be another telling thing, seeing as if there are actually 4 fine structure constants or some version thereof. Now, the second one, so like the first one you get is about like 0.085, yada yada. And then when you square that, you get alpha we're claiming there. The second one is, oh God, I put it in a square root. The root 2 is on the brain. Probably not the worst thing. Okay. And then we've got the second fine structure constant we're claiming, which is 3.66 or so, yada, 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 yada. Okay. Now again, just casual looking, going through some papers. It's like occasionally you'll see like, oh, there's a weird spot in the CMB at about 3.66 degrees Kelvin, something like that. It's I can't understand what's going on. It seems to break from some anomaly. That was probably like 6 years ago. Um, but the interesting thing is, I think if you sum those guys up, you end up getting it was a paper on a lattice structure. But if you search around, I'm thinking we may find some of these other things going around. Like we'll see, like the imaginary golden ratio, which is the cubed root of -1, because I is over here. I is normally defined. The imaginary number. What are you talking about? It's a letter. This is why I say that I think some physicists and mathematicians are some of the best trolls out there, because this is set equal to the square root of -1. So if you actually want to put it in, it would be -1 raised to the 1/2. Well, you could just do the square root. Whereas, the imaginary golden ratio, golden ratio is psi. Yeah, I think it's psi or phi. Imaginary. Yeah, I imagine. Okay, and that's equal to the cubed root of -1. Now, here's the thing. I mean, you can find somewhere on Math Stack Exchange, they explore it. They call it the imaginary golden ratio. I think I submitted it to Team Wolfram for maybe an update, but it's like, all right, you've got this thing. I mean, it's just a continuation, but interestingly enough, if you look through enough papers, and especially on things determining lattice structure and stuff with ice, you start seeing something like this popping up all over the place. I don't call it the imaginary golden ratio. Like if there's an I component, yeah, they'll say the imaginary number I. But you see these things, and you'll see that the -1 raised to the 1/3, the imaginary golden ratio raised to the 1/4, and they'll just list it as quantum operator. It is a quantum operator that comes out there. Very interesting. Why do I say that's also interesting? Okay, slight bit of bias here, because when you take this guy over here, I raised to the j, basically, if you set this, basically, if you take out the 2 pi and you just set it equal to 1, either 1 or 0, where you end up getting the imaginary golden ratio. I think it's, what is it? It's 1 over the imaginary golden ratio plus the uh, imaginary golden ratio, and then some form of those. and everything. So you're basically getting a bunch of imaginary golden ratios out from a very similar structure to that form. Again, that's probably just a coincidence. Not like that's a key clue leading us to some further questions about what might actually be going on. I cannot confirm or deny that. But, oh, yeah, Dubsy. You hungry, kitty? Hold on. Let's do this. All right. So we will go to. Should we go? Hold on. Let's get a hungry kitty, so we'll feed him some tasty snacks here for a second. All right. We'll pay the. Tommy's commenting, discovery is a road paved with ideas that were wrong. Well, I got a lot of wrong ideas. And well, here's the thing. It's like, people are like, well, how could people think that? And it's like, maybe somebody didn't think about that. It's like, I don't know. How many of us were like, you know what I really need? I really need an iPhone or some sort of touchscreen device in order to blow away massive amounts of time and everything. No, we needed creators like Steve Jobs to think of that. I was going to get a BlackBerry at the time. And then I'm like, wait, it's an iPhone 3 for like $99. I guess I'm already stuck to this plan. So, hey, upgrade me, bro. That was how I got into that. But let's see. Well, circles are very interesting, WWKK, because if you actually, what is a circle? It's something. You get its diameter multiplied by pi or 2 of its radii, because we like doing radii, and then you'll get a circle. Okay, you get a string. You hold a string. You go around the string at equal length. You got a circle. But a circle, well, we also use it to represent 0 at times, or at least more of an ellipse there. But a circle, technically, depending on how you want to view it, if you just keep on, if you're an ant or you are a flatlander and you're just kind of like walking along the side of the circle, well, maybe you might even need to just be a one-dimensional creature. But essentially, a circle is going to be infinite. You can just keep on walking around and around and around. So you got a notion of infinity. Now, it depends on how much time you're going to go. Well, then again, time, you could wrap that around length. Why am I thinking of winding numbers right now? Because they describe winding numbers within, I think it was a quantum field theory or something, maybe just space quantum mechanics. Uh, I would ask someone smarter than me more about circles there. But let's see, what do we got? Let's go to. I should have probably played this. This give me a chance to feed the cat. So, since we are going to also be conjecturing here, because that's why I had to say this is how I learn impossible things. I was going to say how to learn impossible things. I'm like, that seems a little melodramatic, or maybe the way I did it was more melodramatic. Oh, cat's coming. So, remember, folks, we're going to conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper Rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper Rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
You timed it just right. Of course you're going to steal your brother's food now. It's okay. It's okay. It's to be expected. But, all right. So now that we're officially conjecturing ahead, again, feel free to trust, but verify. That's one of the big things. A lot of times you see something like, at least for me, I'll still be like, this is exactly what I want to see. And it's like, all right, share. And that's like, seems really much like what I want to see. Let me investigate. Okay, this either looks like BS, or I feel like the title and what actually happened seem to be very different. All right, unshare. What? I mean, if we get new information, what are you just gonna double down on being wrong? Why? Because I can't admit I was wrong. God, who would do that? It would be even worse if people are just doing that because some dude that people associate with an ancient Akkadian emperor statue told them to do that. God, it's a good thing we're not sheeple here. Unless you're an actual sheeple. It's, hey, furries are totally welcome. Hey, look who's talking. We're talking to a scaly dude right here. So it's okay. It's okay. Hey, you can be whatever you want. It's everyone loves to buy. It's, don't force things on other people. That's all I'm saying. I'm just treat people like you would want to be treated. And then people use that inversion to say okay, that's for another thing. I should really start up another channel and just see. This is why I want to get the Physics Monastery on stable ground, stable funding, just so I can get back to bothering the right people. That's a terrible personal goal. Might be an honest goal. So, kind of like what I was complaining about earlier. All right. All right. So I'm going to really quickly go over, for my own practice, the stuff on the board because we were talking about it the other day. All right. So again, this is my practice. Take it with a grain of salt. Let's see if we can figure out some of the stuff on the board here. All right. So I got our standard little equation thingy here, and then we found very interesting things because on that poster there, we have the universal parabolic constant divide by 8. So in our mind, it's like, all right, so like pi has to do with circles. The universal parabolic constant, or PUP, is has to do with parabolas. It's basically got a similar ratio-based relationship. 8 is basically what we're claiming for the number of derangements of mass itself. And what do I mean by that? Because our different Planck units, this is the method by which Dad had claimed logarithmic based closed forms for the 5 Planck constants. So basically, you get I'll just do it over here. T sub p, L sub p, Q sub p, M sub p, big T sub p, and that was for the Planck time, the Planck length, the Planck charge, the Planck mass, the Planck temperature, and the derangements we're claiming are the magnitude of the exponent there. So Planck time is approximately about 10 to the minus 44. So the absolute magnitude of minus 44 is 44. Absolute magnitude of Planck length is about 10 to the minus 35. So that's 35 derangements. Planck charge is 10 to the minus 18. So that'd be 18 derangements. Planck mass is 10 to the negative 8. So we would have 8 derangements. And then the Planck temperature is about 10 to the 32. So the magnitude of that is 32 derangements. So that's the claimed way of the number of ways you can organize a different thing. And that is also equal to the total number of dimensions, which is the subfactorial of 5. So that's that exclamation point 5. So not 15. You just do exclamation point 5 because you really mean it. Okay. So the whole interesting thing about this led to another discussion. So before we're just kind of going over here, we're looking at different roots, and then you're finding it's like, all right, you have a unit 1 over here to these parts of the hyperbola, and then it's like, all right, but the hyperbola each has a foci, and that foci is at root 2 over here, root 2 over here for your x and y axis, and then over here you got negative root 2 and negative root 2 for your foci over there. Okay, so basically we're just mapping out the territory, or we're attempting to map out the territory based upon the calculations and the model we're working with. That's what you do with any model. There's plenty of folks working on different models. You do you, boo. I just happen to find that I'm like, all right, well, if I'm looking to get back into science, well, number one, that actually responded. Not everybody responds because a lot of people are busy and everything, especially, like, let's say, if you're a famous scientist and you use social media and someone comes across something, they think it's so fantastic and they're like, this person, oh, they need to know this and everything. And you're a professor and you're getting sent. Professor Wolfram has publicly said he gets like 600 emails a day. And How many of them are from his actual job, his friends, and then just randos on the internet? He responded to at least one of those randos. By he sent it over to his assistant, and we hashed out a thing, and he came on the show. So, uh, thank you to all those who were involved. Okay, but if you're getting sent all these things, it's like okay, because at first, like the whole reason, it's like, oh, this guy solved the. He was able to calculate these things. How can you calculate all those things and everything? It's like he seems to be doing it in a way that I can understand. Why? He's using like multiply, divide, addition, subtraction, and stuff. Occasionally, you could write it as an integral or something like that, but those are usually interesting relationships. But it seems much computationally reduced. Why? Because we only have five basic ingredients. There are five-dimensional ingredients. We got our stuff, and we take that stuff, and then we do some fancy math. Sometimes we multiply it by 2 pi, so we're multiplying it by a circle. Sometimes we're dividing it by a circle. Sometimes we're squaring some things or cubing some things. It's like, okay, if you've gone through math in high school, you've probably seen some of that stuff. And if you went through some decently advanced math in high school or maybe a little bit of college math, um, good chance you've probably done math harder than this. So it's also a personal perspective. Oh, that and the other thing that helps make things possible. Remember, human beings can't fly unless you buy a plane ticket or have your own aircraft and requisite fuel and everything like that. It's like, yeah, so human beings ourselves, yeah, waving our arms usually doesn't work. Might terrify other people as the scent from our armpits wafts around. It's a good thing that there's no other humans here right now. I'll tell you that. But we don't do that, but we can leverage technology. We can leverage technology. And historically, you remember seeing, like, was it the Wright brothers and stuff? They finally got their things. That's originally people were trying to, oh, we need to be like birds. We need to fly like birds. And you realize, wait a second, if we are able to get our wings in a certain way, and we're able to displace so much air, and we're able to create little vortices because of the pressure gradients going along the wings, and then we have some power pulling us forward, pushing us forward, whatever it might be, we can generate lift. And then we can cram in like sardines to an aluminum tube, fly at 30,000 feet, and get from coast to coast in it was about 10 hours. It's about 8 or 9 hours from Massachusetts to Salt Lake City, and it's like 5.5 hours going the other way because I guess the Earth is running or spinning below us a little bit there, so it seems faster. Uh, and then we add in time zones, and nobody ever gets confused about those. And let's not talk about daylight savings time. Ranted about that enough before, but okay, we've leveraged technology. The whole point of that 2-minute misguided metaphor is we actually have tools now we can use to do very interesting things. What are some of the interesting things we can do? Well, it's basically the prime workhorse. So I might actually make a tab. We got certain tools, and especially the price is right and they're free, like Wolfram Alpha. What's this? Okay, so our first little thingy there, as we can see, we got set to 44, and this is the claimed logarithmic closed form for the Planck time. So what we got here? We got a pi. We're solving for the x there. So pi times the base of natural logarithms times hyperbolic sine squared of 1/4. That sounds pretty orthogonal to me. And we just set it equal to the magnitude of the claimed number of derangements. The magnitude of the exponent in the Planck time is -44, so that'd be 44 there. Gives us these other forms. Here we in logs for our real solution. And then we get as many digits as we would like for the Planck time. And then you just multiply that by 10 to the -44. That's the claim. Seems to work pretty well. Again, don't have to agree. It's you use whatever you want. If you want to use that to get some extra digits to use for your scalar, by all means, have a good time. But we have tools like this that are free, or you could pay for it. And I could sign in, we could use Pro and use more computation time and maybe use some of the new features that are coming out. But now we have the ability to, and even back in the day, even if you had the information, what's the mass of the electron? Well, back in the day, you'd have to have the journal, look at the updated experiments, see if we have more significant digits, have to type in all those digits and everything, blah, 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 go through all those digits, do multiplication by hand or with a calculator, or put in note cards and then insert those note cards on the computer. It's like, oh, what is the electron? Electron mass divided by the proton mass. Oh, look, it comes up because I've done that before. And it gives us, ooh, yeah. I was not expecting that. I usually look at it as the inverse. Oh, that's a lot of significant digits. What happens if I want to look at the opposite? 1 over. Shortcut. Oh. As a unit? There we. Oh, I was thinking electron muon mass. I'm like, why does it not say 206? See, I I asked the. All right, 1836. Yeah, there we go. Cool. So now you can see that number, and it's not just 1836. We got an extra 5 significant digits on that. So we got like 9 significant digits between the mass of the electron and mass of the proton. And to be fair, seeing as we have those masses too, 12 significant digits. Although the last couple of significant digits have gone up, have gone down. There's about 4.5 sigma swing last codad update for the mass of the electron, mass of the protons. Swung by about 4-ish, maybe 4.2. At least the mass of the electron. That led to a much better answer. It's that stronger, much stronger confidence in that answer because it seems to self-close. Okay. I've been rambling on a little bit. What do we got? Oh, we got some other friends joining. Let's see. What do we got? And we have, oh, excuse me. We've got Quantum Age Comics. Ooh, folks from the comic side of things. I haven't spent enough time. God, I need to redo my whole webcomic with Piper there, Breaking the Multiverse. Why? Because we're just going to do a lot of the same thing. And hypothetically, let's say, okay, this is a side tangent. Do I still have the website? God, I'm so late. What is it? Making. I still have the site. We haven't uploaded anything to it in ages. Yes. It's literally what it looks like. It's the same. It's sort of breaking the multiverse. Okay. Yeah, gotta start that webcomic. Actually, and by that I mean I actually need to do things. So the editor and slash illustrator could edit and illustrate. But what I'm saying is we now have tools that back in the day, literally, you need to be a smart person that was dealing with these things to know that these things existed. Okay, that's number one. Number two, you need to know like the right things. You can have access to the different journals, get those different experiments. You need to put them in. You need to look for the relationships. You're talking about a massive time sink right there. Whereas, at least for a decent first level approximation, I just go right into Wolfram Alpha, use the electron mass, the proton mass, 1 over the Planck energy, and see all these phenomenal relationships and stuff like that. Oh, let me show this last time, just because here's the thing. It's like, regardless of any papers that I write or anything like that, it's like a lot of this is just noticing things. It's like, all right, I got the Planck energy. There's a Planck energy. This thing you right here. All right. Oh, Planck mass times c squared. Duh. All right. So it gives you this in joules, it gives you the electron volts, blah, blah, blah. And then it's like, all right. What happens if I do 1 over that? Oh, that's a number. Okay, reciprocal joules. Wait a second. Inverse energy. But that number and that magnitude look kind of familiar. So I'm like, all right, well, let me just click on this. And rather than it be reciprocal, What is that in actual joules? Just curious. All right. It's key electron volts. All right. Because your relationship of masses of different particles, give you the dimensions right there, the relativistic mass equivalent. And it's like, wait a second. Maybe there's a different dimension. What if I do like meters cubed? Oh, very interesting. The inverse of the Planck energy, if you were to just strip off the reciprocal nature of it, and there are other mathematical ways you can do that, it's pretty darn close to the universe vacuum energy density. Wait a second, I thought that was a catastrophe or something. Why does it seem to be so darn close? Now, and again, we also have, where was it? Let's go to our friend. I mean, that was just like noticing little things like that. Eventually, it's like, all right, I just bookmark something. Literally, I will physically bookmark and mentally bookmark something in my head. And it's like, all right, maybe I notice this late at night. Maybe I don't know the proper question right now. Wait a second. So that is too complicated. Yeah, I've gone through a number of different calculate. There we go. All right. So that was how I kind of played around, got this little guy here. It's like, all right, I was trying to do another way to potentially verify the mass of the Higgs to see if I get the same answer. I failed. And eventually it's like, wait a second. So if I take the relativistic equivalent of joules, basically the mass equivalent in 1 joule of energy. You just divide by c squared, you get the energy out. So you just related with kilograms. It's about 1 to the minus 17 kilograms. Okay. You set that equal to the Planck mass. And we're solving for x. And you just need your pi divided by 3 term there. Gives us this answer. And we were solving for kilograms. Algebra. It's algebra, my friends. It's just algebra. We plug that in there. So that was kilograms. So do kilograms. And then you can put meters in it, but it makes it less pretty in the calculation. So you can add them after. It gives you the same answer. And again, please verify me. Oh, wait a second. Kilograms divided by me. Oh, all right. That's very interesting. Equals, the dark energy mass density. Wait a second. The mass density of dark energy? How very interesting. So what happens if we just go back here? So rather than solving for that, we can just do a little friend over here. Oh, hold on. What's for this guy? So rather than that, okay, we don't want mass. Let's just do energy. Let's just look at 1 joule. You see, look, I'm putting the 1 there, so we don't disagree. 1 joule. Since we're looking for energy now, we just do Planck energy. And we're taking square root of that. Hold on. I'll just put these guys over here. So it makes it prettier, in my opinion. Okay, so what do we got now? Now we're solving for 1 joule of energy. We're searching for within the geometric mean. What we're doing is we're multiplying 2 things together, and we're taking the square root of our expression here. Okay. The square root of the Planck energy, and then we're going to solve for x kilograms. So we get, oh, hold on. Oh, I did that wrong. Excuse me. GeV. Because we're doing energy. You want to have the same units. Otherwise, you're going to be like, oh, God, why is nothing working? All right. So we got 1 joule. So that's an energy term. And we get that set equal to the Planck energy. And then we're solving for this other unit of energy because we have giga-electron volts there. And the relationship between those two is literally divided by pi divided by 3. Within our geometric mean, we let Wolfram Alpha do all the hard calculations, and we get 3.341. That's GeV. I just click on that. We add in our dimensional unit, GeV. We're searching for volumetric density. So there'll be energy divided by meter squared. And happens to be approximately the universe vacuum energy density out of 1 joule. Imagine my shock. And again, I don't know if that's right. We're going to need much better precision measurements. We're going to get about two, maybe three-ish significant digits or so there. And that most all that from the Planck 2015 at 2015, 2018, because the Planck satellite was only operational for like 3 years. But we got a whole buttload of data, and people are like still going through it and everything. So if we could have some new measurements for the vacuum energy density and get some more significant digits, hey, maybe some of that stuff will pan out statistically. Probably wrong, but it's at least within the magnitude, and maybe it's a slightly different expression. I guess we're going to have to see. Again, we follow the evidence. Because my old man, God rest his soul, he was an attorney. He always told me this: number one, the truth is the ultimate defense. And number two, you follow the evidence. Now, the evidence doesn't always go in ways that we hope it would go. Now, I accept that, and that's what you're supposed to be a good scientist. If you have a reason why we're deviating from experiment and observations, that's fine. But if we want to be less wrong, we need at least attempt to be a little bit more right. And how do we do that? Well, it might depend on who you're asking. So I realize I didn't explain a lot more of these things. We'll get into that maybe tomorrow or something, because I know we found a very interesting thing over here with the. It appears to be a balance point in the zeta function. Maybe Thad would like to talk about that at some point when he gets back. But been going for over an hour already, so well, that's okay. But that's about all for now. So hey, take care of yourselves, everyone. It's a crazy world out there. But other than that, peace out, and we'll see you all tomorrow. Bye.